In the world of artificial intelligence and technology, we often hear the term neural networks. It's a concept that, while intimidating at first, holds the key to our tech-driven future. But what exactly are neural networks? How do they work? What are their types? And more importantly, how can you build one? Well, here's everything you need to know about this amazing technology, explained in simple terms. Let's start. What is a neural network? Picture a team of workers, each specializing in a particular task, but also able to collaborate to complete a complex project. That's essentially how a neural network operates. It's a sophisticated computing system modeled after the human brain, with layers upon layers of interconnected neurons working together. A neuron is simply a small computational unit that takes in inputs and generates an output. When combined in the hundreds or thousands, they create a neural network, capable of learning and making decisions. How neural networks really work. Imagine you're teaching a child to identify apples. You show them pictures of apples, tell them these are apples, and correct them when they make a mistake. Over time, they start to recognize apples on their own. Neural networks learn in a similar fashion, albeit in a more mathematical way. Information is fed into the network, processed through various layers of neurons, and an initial prediction is made. This prediction is compared against the correct answer, and if it's wrong, the network adjusts its internal parameters called weights and biases to improve the prediction next time. This process, known as training, is repeated with many examples until the network can accurately make predictions on its own. What makes neural networks so powerful? Let's think about a detective trying to solve a mystery. They would gather various clues, analyze them, and draw conclusions to solve the case. What if there are hundreds of clues and multiple mysteries to solve simultaneously? A human might struggle, but a neural network excels in this. It can sift through mountains of data, recognize complex patterns, and draw accurate conclusions. For example, a neural network can process all the pixels in an image, the clues, recognize the complex patterns, facial features, and accurately conclude who the person in the image is. That's the power of neural networks. They excel at identifying patterns and making decisions, even in complex scenarios where humans might struggle. The different types of neural networks. There are many different types of neural networks that can be used to solve various types of problems. Common types include convolutional neural networks, recurrent neural networks, and generative adversarial networks. Here's a simplified explanation of each type. Convolutional neural networks, CNNs. CNNs are a type of deep learning model primarily used for image processing, though they can be used for other types of input as well. They're called convolutional because they use a mathematical operation known as convolution to process input. Convolution involves applying a filter, or kernel, across the input data to create a processed output. This enables the model to automatically and adaptively learn spatial hierarchies of features. For instance, in image classification, lower layers may learn to recognize simple patterns such as edges, while deeper layers recognize more complex patterns. CNNs have been instrumental in tasks such as object detection, facial recognition, and even medical image analysis. Recurrent neural networks, RNNs. RNNs are used for sequential data processing, where the order of the data matters. Examples include time series prediction, natural language processing, and speech recognition. Unlike traditional feed-forward neural networks, RNNs maintain a kind of memory by feeding the output from a given layer back into the input of the same layer for the next step in the sequence. This recurrence forms an internal state of the network, which allows it to exhibit temporal dynamic behavior. A major issue with standard RNNs is the vanishing gradient problem, which hinders them from learning long-range dependencies. To overcome this, variations of RNNs, such as long short-term memory (LSTM) units and gated recurrent units (GRUs), are often used. Generative adversarial networks (GANs). GANs are a class of AI algorithms used in unsupervised machine learning. They are designed to generate new content that is similar to some existing content. The model is composed of two parts: the generator, which creates new data instances, and the discriminator, which tries to determine whether each instance of data it reviews belongs to the actual training dataset or was created by the generator. The two networks compete in a zero-sum game, hence the term adversarial, leading the generator to produce increasingly realistic outputs. GANs have been used to generate realistic images, music, speech, and text. With that said, here comes the next section: the role of neural networks in AI. Neural networks play a fundamental role in the field of artificial intelligence, providing the foundation for many machine learning algorithms and systems. Here are several key roles they play. Number 1. Data processing and feature learning. Traditional machine learning algorithms often require manual feature engineering, where humans need to specify what aspects of the data are relevant for solving a problem. Neural networks, on the other hand, learn these features automatically from raw data, which is a process known as representation learning. This makes them extremely versatile and capable of working with complex, high-dimensional data such as images, audio, and text. Number 2. Function approximation. Neural networks are universal function approximators, meaning they can model complex, non-linear relationships between inputs and outputs. This makes them suitable for a wide range of tasks, from predicting house prices to classifying images. Number 3. Sequence processing. Some types of neural networks, like recurrent neural networks (RNNs), are specifically designed to handle sequential data. They are capable of processing variable-length sequences and maintaining internal memory of past inputs. This makes them useful for tasks like language translation, speech recognition, and time series prediction. Number 4. Generation of new content. Generative neural networks, like generative adversarial networks (GANs), are capable of generating new data that resembles the data they were trained on. This allows for the creation of realistic synthetic images, music, and even text. Number 5. Decision-making and reinforcement learning. Neural networks are used in reinforcement learning as function approximators to estimate the expected return, value function, or the optimal policy function. These models are at the heart of advanced AI systems that can learn to play video games, control robots, and even play board games at a superhuman level. And that leads us to the next section: how to build a simple neural network. Building a neural network involves several steps, and it's not that simple, especially for beginners. However, we'll outline a simplified version of the process to help you understand the full picture. Step 1. Define the problem. What are you trying to achieve with your neural network? This could be anything from classifying images to predicting stock prices. The type of problem you're trying to solve will dictate the kind of neural network and the kind of data you'll need. Step 2. Gather and prepare your data. Collect relevant data for your problem. You'll need to split your data into at least two sets: a training set, which the neural network uses to learn, and a test set, which is used to evaluate how well the network has learned. Sometimes a third validation set is used to fine-tune the model parameters. Step 3. Design the neural network architecture. Decide on the structure of your neural network. This includes the number of layers in the network and the number of nodes in each layer. For a simple neural network, you might start with an input layer, one hidden layer, and an output layer. The input layer size corresponds to the number of features in your data, and the output layer size usually corresponds to the number of classes or the type of prediction you're making. Step 4. Train the network. Use your training data to adjust the weights and biases in the network. This is usually done using a process called backpropagation and an optimization algorithm like gradient descent. The objective is to minimize the difference or error between the network's predictions and the actual values. Step 5. Evaluate the network. Use your test data to check how well your network is performing. This step helps ensure that your network is not only memorizing the training data, overfitting, but can also generalize to unseen data. Step 6. Iterate and improve. Based on the performance of your network on the test data, you may need to go back and adjust your network's architecture, gather more data, or tweak the learning process. This is usually an iterative process. And now comes the big question: what's the future of neural networks? Neural networks have come a long way since their inception, evolving from simple feed-forward networks to complex structures like convolutional neural networks, CNNs, recurrent neural networks, RNNs, and transformers. It's expected that this evolution will continue, with future research likely to bring about even more refined and specialized architectures to tackle a diverse array of challenges. One of the main focuses in the development of neural networks is enhancing their transparency and explainability. As these models become more intricate, the reasoning behind their decisions becomes harder to understand, leading to the challenge of black box AI. This is a pressing issue, especially in sensitive domains like healthcare or finance, where comprehending why a certain decision was made by the AI is critical. In parallel, there is an increasing emphasis on making these networks more energy efficient and reducing the size of the models. State-of-the-art networks today are sometimes excessively large and require vast amounts of energy for training. Therefore, the creation of compact, power-saving models and the development of methods to train them in a more efficient manner is an area ripe for future exploration. Another fascinating area of research is enabling neural networks to learn from a minimal number of examples, also known as few-shot learning, or even to make accurate inferences about never-seen-before classes, termed as zero-shot learning. Humans are naturally capable of learning new concepts from a few instances, and improving the ability of neural networks to replicate this will be a key development. The field of generative models, particularly generative adversarial networks, GANs, which have seen success in generating convincing synthetic data, also hold a promising future. Advancements in this area could lead to more realistic virtual environments, the synthesis of personalized avatars, and maybe even the creation of AI-driven art. Looking at even more advanced concepts, we find research areas such as neuromorphic computing and spiking neural networks that attempt to mimic the structures and signals of the human brain. These technologies could offer unprecedented efficiency and capability to neural network processing. If you've made it this far, comment down below with the word 100% to confirm that you've received the knowledge from this video. For more interesting topics, make sure to watch the recommended video that you see on the screen right now. Thanks for watching.